Welcome, learners. My name is Teacher Samuel Macharia. I have taught chemistry for quite a long time. I have produced the results in the KCSE, and I want to take you through some topic in chemistry, a Form 4 topic. I want to make sure that by the end of the topic, you have understood all what this topic entails. I want to make it as simple as possible. I want to make it palatable so that by the end of this topic, you will consider chemistry as your booster subject. Welcome. Like I said, our topic today is electrochemistry, a Form 4 topic. And when we look at the word electrochemistry, it looks like it's a combination of two words, that is electro and then chemistry. Therefore, when we look at the definition of electrochemistry, it means it is the chemistry of electron transfer in electrochemical reactions. Electrochemical reactions deals with the relationship between electrical energy and chemical reactions. Essentially, electrochemical reactions are redox reactions. In Form 1, I remember we say that redox reactions are reactions that involves both the reduction and oxidation taking place at the same time or simultaneously. Example of redox reaction that I want us to consider are one, I want us to consider displacement reactions. And the first type of displacement reaction I want us to consider is the displacement reaction between metal and compound of other metals in solutions. Example 1. I want us to look at the reaction between iron metal and copper 2 sulfate solution. As indicated in the reaction below, where the iron metal combines with copper 2 sulfate solution, because iron is more reactive than copper, will displace copper out of the solution to form iron 2 sulfate, and copper metal moves out as a solid. I want to pose a question here. When you look at this reaction, using your previous knowledge, can you be able to determine the oxidized substance and the reduced substance? Definitely, I know you can. When we look at the change that is taking place, iron metal is converted to iron 2 sulfate. So essentially, using our previous knowledge, we can look at iron metal is oxidized to iron 2 sulfate. One, we can remember in Form 1, we said oxidation is addition of oxygen. So of course, here, oxygen has been added. So using that simple knowledge, we can talk about this one as oxidation. Though, there is another element which is added, which is sulfur. So we are going to further this definition of oxidation, because now we can see it is not only oxygen which is added. So I now want us now to look at this reaction critically. And I want us to look at the ionic equation emanating from this reaction. I want us to take back and reflect on how we were writing ionic equation. What we do is we look at the substance that is in aqueous state, like the copper 2 sulfate. We separate it into the constituent ions. For example, copper 2 sulfate has copper 2 positive ions and sulfate 2 negative ions. Then the iron 2 sulfate solution can be separated into iron 2 positive ions and then sulfate 2 negative ions. So now, after separating the solution into the constituent ions, we can now see that the sulfate ion is common on both sides. We consider those ions that are common on both sides as spectator ions. I want us now to cancel out the spectator ions, the sulfate that is. So this sulfate, we cancel it, and we also cancel it on the other side because they cancel one another. That one takes us now to look at the remaining substances. We have iron metal solid, that one you don't touch. We have now here copper 2 positive ions in aqueous remaining. Then on the other side of the reactant, we have iron 2 positive aqueous remaining, and then copper solid. During this reaction, the observation that occurs is that the gray solid reacts to form a brown solid. Then the blue solution changes to form green solution. Now, I want us to look at the change that takes place in the reactants. The iron metal is converted to iron 2 positive, that is cations. We know that metals, when they are converted to cations, there is loss of electrons. For example, iron loses 2 electrons to become Fe2 positive. So there is loss of 2 electrons. I want to take you back. Previously, we said iron metal is the one which is oxidized to iron 2 sulfate, where we have iron 2 positive ion. So meaning that one can give us now the new definition of oxidation and reduction in terms of electron loss and gain. For example, if you look at the change of iron metal to iron 2 positive, there is loss of electrons. And we said that is oxidation. So oxidation is loss of electrons. In short, we can use the initials OIL, oil. For oxidation is loss of electron, oil. Then we say that the copper 2 is reduced to copper metal. That is the reduction. And in the reduction, there is gain of electrons. So reduction is gain of electrons, Lig, Lig. So we can now see oxidation being loss of electrons, we use the word oil. Then reduction is gain of electrons, we use the word Lig. So we can use the oil and Lig to help us remember the definition of oxidation in terms of loss of electrons and reduction in terms of gains of electrons. Let's further our work. Now we say that iron is the oxidized species. When we look at iron being oxidized, it is oxidized by the copper because that is the other reactant that it reacts with. So copper 2 ion is the oxidizing agent. So now we can see that the species that gains electron is the oxidizing agent. In this case, it is copper 2 positive ions, which is the oxidizing agent. We also saw that copper 2 is the reduced species. Copper 2 positive is the reduced species, meaning the reducing agent is iron metal. And what does the reducing agent do? This is the species that loses electron. It is the reducing agent. And therefore the reducing agent is iron because the reduced species is copper 2. I want us to have another example of this displacement reaction. And to get an eraser, please. Thank you. Let us have time. We erase those marks. Thank you. We still get our highlighter. Then we look at the next example of reaction for displacement. Reaction between zinc metal and copper 2 sulfate solution. Of course, because zinc metal is more reactive than copper, it displaces copper out of solution to form zinc sulfate and copper solid. The observation here is that the gray solid reacts to form brown solid, then the blue solution fades towards colorless. When we look at the two changes that takes place, of course, now with the help of the ionic equation, the zinc solid is converted to zinc 2 positive, whereby there is loss of electron, and that is the oxidation. Then the copper 2 positive ions gains the electrons, so it is the one which is undergoing reduction to form copper solid. Similarly, we can also look at example 3, and I would like you to use the previous two examples to also discuss by yourself during your own free time about this displacement reaction, and you show the oxidation and the reduction change. I want us to now conclude. We have seen that those metals that are more reactive will displace the less reactive metals. And the most reactive metals are the ones with higher ability to lose electrons. And therefore, the more reactive metal is a stronger reducing agent. And therefore, the weaker an oxidizing agent it is. I want us now to look at something else, another term we call oxidation number. Now, oxidation number, it is the apparent charge that an atom has in molecules, ions, or in compounds. For example, in monoatomic ions, the oxidation number is equal to the size and the sign of the charge. For example, if we look at aluminum ion with the symbol Al3 positive, its oxidation number is positive 3. If we consider magnesium ion Mg2 positive, its oxidation number is positive 2. If we look at sodium ion Na positive 1, its oxidation number is positive 1. Now, oxidation number will help us track the movement of electrons in redox reactions. And therefore, let's come to the definition of oxidation and reduction in terms of oxidation number. Now, oxidation number is the increase in oxidation number. Oxidation is the increase in oxidation number. And then the reduction is the decrease in the oxidation number. I want us now to look at some rules that we use to assign oxidation number. First rule, oxidation number of an uncombined element is always equals to 0. Then number 2, the charge on monoatomic ion is equivalent to the oxidation number of that element. For example, the one we have given for aluminum 3 positive, the oxidation number is positive 3. The oxidation number for hydrogen in all compounds is positive 1, except in metal hydrides, where it is negative 1. Then number 4, the oxidation number of oxygen in compounds is -2, except in peroxides, where it is -1, and oxygen fluoride, where it is positive 2. In complex ions or radicals, the overall charge is equal to the sum of the oxidation number of the constituent element. In compounds, the sum of the oxidation number of all constituent atoms is equal to 0. I want us now to have some worked example. Example number 1, let's see how we can calculate the oxidation number of nitrogen in the following. Now, we start with nitrate ion. We know the symbol of nitrate ion. It's a complex ion. It's a radical NO3 -1. To calculate, then we just know that when we add up all these oxidation numbers of the constituent elements, the total sum equals to -1 or -1. So now, nitrogen, we don't know. That is why we write N plus into bracket oxygen. The oxidation number of oxygen is -2 or -2. You multiply by 3 because there are 3 oxygens, close the bracket, equals to -1, which is equivalent to the charge. Then when we use body mass, work out inside the bracket first. -2 times 3 is -6. So N plus -6 equals to -1. Then we know that positive and negative will simplify to negative. So N minus 6 equals to -1. And therefore, when we take -6 to that side, it becomes positive. So N equals to -1 plus 6. Whereby now, if we simplify, N equals to +5. We don't write 5, but we write +5, being the oxidation number of nitrogen in the nitrate. And therefore, note, in the formula of nitric acid, HNO3, with the nitrate ion as a radical, it is called nitric 5 acid, since the oxidation number of nitrogen in it is +5. You can also use the same working to work out the oxidation number of nitrogen in the nitrite. I will want to leave you to do that one as assignment for practice. But I want us now to look at the next one, which is NO2 with no charge. I want us to do the calculation. I want to get a pen here. And then NO2, I want us to start NO2. If you look at this one, there's no charge. So this is a compound where the overall charge is 0. So if we add up all these oxidation numbers, we get equals to 0. So we start working. Nitrogen, which is N plus, now we put brackets. Now we come to the oxygen. Oxidation number of oxygen is -2. And because there are 2 oxygens, you multiply by 2, close the bracket, the total sum equals to 0. There is no charge. Now, when we work out inside the bracket, -2 times 2 is -4. So we are going to have nitrogen N plus -4 equals 0. So when we take -4 to the other side, it becomes added. So nitrogen equals, let me get the pen again, sorry. Equals 0. 4, meaning now 0 plus 4 is plus 4. So meaning that the oxidation number of nitrogen here equals to plus 4. And if you can recall very well, we know that the UPAC name for this compound is nitrogen 4 oxide. Nitrogen 4 oxide. And you can see that the oxidation number of nitrogen is positive 4. And the compound is called nitrogen 4 oxide. Thank you. Now you can do the other one as assignment. I want us to continue. Now we go to the second example whereby we are required to determine the oxidation number of sulfur in each of the following species. For example, in the sulfate SO4 2 negative, the working is there, sulfur S plus into bracket, the oxidation number of oxygen is -2 times 4 because there are 4, close the bracket, equals to, the charge is -2, so equals to -2. -4 times -2 times 4 is -8. So S minus 8 equals to -2. And you take -8 to the other side, becomes added. So when you work out the oxidation number of sulfur S equals to +6. Now, the UPAC systematic name for this sulfate, this one here, is called sulfate 6 because the oxidation number of sulfur is +6. Sulfate 6 ion. The oxidation number of sulfur is +6. So this is sulfate 6 ion. Now, I want us now to look at the other one, SO3 2 negative. You work out the oxidation number of sulfur as we have worked out in the sulfate. At this time, the oxygen are 3, so you ensure that -2 you multiply by 3 equals to -2. I'll leave you to do that one. But I want to do the number 3. I want to do number 3. Let me get the pen. Before I get the pen, I want to lab my working space. Lab. We lab the previous working. Lab the previous working. Thank you. So let me get the pen again so that we work out this one. So for SO2, like we did with that one, SO2 we have sulfur S plus O, okay, you put bracket, oxidation number is -2, multiplied by 2 because there are 2, multiplied by 2, bracket equals 0 because it has no charge. Then, like the other one, -2 times 2 is -4, so it's plus -4 equals 0. So meaning this one becomes -4. When you take it to the other side, it becomes positive. So it's 0 plus 4, meaning that S equals to positive 4. And that is why, if you can recall very well, the UPAC systematic name for this compound is sulfur 4 oxide. I want us to do the same working with the next compound, SO3. We get the laser, and I love this. And this working so that we do the other working. So we now work out for SO3. So SO3, because we now see that we have S plus into bracket. The oxidation number of oxygen is -2 multiplied by 3. There are 3, close the bracket, equals 0. Then, like the other one, -2 times 3 is -6. So S plus -6 equals 0. So when you take -6 to the other side, so S equals to sorry, let me get a pen again. Sorry. Equals 0 plus 6, meaning S equals to positive 6. So, but sure. So the oxidation number of sulfur in this compound is +6. And that is why when it comes to the UPAC systematic name for this compound, we call it sulfur 6 oxide. Sulfur 6 oxide. I want us to clear this, okay, so that we look at something else. We clear that, then we look at something else. Go to the next example. Example number 3. Now you are required to determine the oxidation number of manganese in each of the following substances. We also are required to give the UPAC systematic name after working out the oxidation number of the central element. Now, first one, MnO2. We do the working of the oxidation number of Mn, manganese. So like here, manganese, we don't know, plus into bracket, oxidation number is -2 times 2 because there are 2. And because it has no charge, the total equals to 0. So this is -4 equals to 0. So Mn -4 equals to 0. We take -4 to the other side. So Mn equals to 0 plus 4, meaning that Mn equals to +4. And that is why the UPAC systematic name for this compound is manganese 4 oxide. Then we can also look at the other compound, Mn2O3. You can also do the same working and work out the oxidation number of manganese, Mn, in this compound. I'll leave you to do this one. Then you also come up with the UPAC systematic name. I want to work out together with you the oxidation number of manganese in part 3. Now, let me get a pen as usual. So we are now on working out the oxidation number of Mn in this compound. So we start, we have Mn, we don't know its oxidation number, plus oxygen. Now we put brackets. Oxidation number of oxygen is -2. And because they are 4 oxygen, you multiply by 4. The bracket, the total equals to the total charge, which is -1. So use body mass. -2 times 4 is -8. So we are having N plus -8 equals, I like the working, -1. As you can see here, -8 can be taken to the other side. So you're going to have Mn equals -1 plus 8. So we simplify, -1 plus 8 is +7. So finally, Mn equals +7. Correct. I know you were working with me and you also got the same. Meaning now let's come to the UPAC systematic name of this ion or this radical. In fact, we call it manganate 7 ion. Manganate 7 because the oxidation number of manganese is +7. So we call it manganate 7. And now this compound here, KMnO4, we call it potassium manganate 7 solution compound. Potassium manganate 7. That is the UPAC name for that compound. The ion is called manganate 7 ion. Let's move on. I want us now to go to fourth example. Now, I want us now to look at the fourth example. You're supposed to determine the oxidation number of chromium in each of the following substances. And similarly, you also give the UPAC systematic name. The first one has been worked out for us. Sorry, let me go through it. So we have chromium, Cl, plus, into bracket, we know that the oxidation number of oxygen is -2 times 3. I know you can follow this one, equals to 0 because there's no charge. And then you do the working and you get that the oxidation number of chromium finally is +6. And that is why we call this compound chromium 6 oxide. Chromium 6 oxide. Chromium 6 oxide. Now, I want us now to leave number 2. You can practice doing it during your own free time. I want us to do together with you number 3. Let me get the eraser. First of all, we erase our working space. We erase so that our working space is clear. Get a pen. Which the pen is here with me. Now, we want to do oxidation number of chromium in this compound. So we are having here chromium Al2. So Cl, they are 2 plus into brackets, because we know that the oxidation number of oxygen is -2. So -2, you multiply by 7 because there are 7 oxygens. The bracket equals the total charge is -2, so equals to -2. Then we come to the working. -2 times 7 is -14, as you can remember. So the chromium, 2 of them, plus -14 equals -2. Now, you take -14 to their side, so you are going to have the chromium, 2 of them, equals -2 plus 14. Now, when you work out -2 plus 14, you get +12. So the chromium, get the pen again, sorry. Chromium, 2 of them, equals to +12. We said slow but sure. And because these are 2, what about for 1? You divide by 2 so that you get the oxidation number of 1 chromium. So divide by 2 both sides. Divide by 2 both sides. So the 2 cancels. And here you get that for chromium is equals to +6, because +12 divided by 2 by 2, 1, by 2, 6, +6. And that is why the UPAC systematic name for this ion, we call it dichromate 6. Dichromate 6. Dichromate 6. So this compound is now called potassium dichromate 6. Thank you. That is the end of the first part of this topic. Watch out for the rest of the topic in my next video. Goodbye.